Hey guys, so next lesson coming at you. So we're going to focus in a little bit on kind of a new topic, which is what we're going to call intermolecular forces, right? And ultimately, we're trying to come around, right? Do a full circle. So we're going to relate the structure of a compound or molecule, right? So those Lewis structure we've been drawing, the polarity, all that stuff, to the properties of solubility, aroma, melting, boiling point, and electroconductivity. We're not going to cover all of those right away, but we're going to start this discussion. All right. So put it all together. What have we already learned? Right. We've already learned about the different types of bonds, whether they're ionic, polar covalent, or non-polar covalent. We've learned that different bonds have different properties. That's one of the very first things we learned. Now, we also then took the next layer there and added how to predict the formula, right? So if I tell you ask you the formula for calcium chloride, right? You'd be able to tell me that that's CaCO2, right? Then we learned how to do Lewis structures for ionic and covalent compounds. And then we learned how to apply those structures of those Lewis structures to figure out symmetry or asymmetry, and therefore whether or not the molecule itself has an overall polarity. All right. Now, we want to try to turn this into some useful information. Now, it's not that understanding how the natural world works and chemistry works isn't in and of itself intrinsically valuable, but ultimately we want to get to a point where we can take this information and put it towards something maybe a little bit more utilitarian in nature, right? So how is knowing this useful to a chef or to a pharmacist or a doctor or an engineer or even someone who does house cleaning and home cleaning, right? How do these things come together in a way that we can make use of that information for our daily lives? All right. So again, it comes back to the properties of these materials. How can we take what we know about the way these things bond, right, in order to predict their properties and then make use of those known properties? All right. So we're going to go back and revisit these things in a slightly different way. So ionic compounds, right? So we already modeled together, right, how to write like a Lewis structure. So the way we model the bonds that occur between, let's say, calcium and chlorine, for example, right? Calcium has 2 electrons with which to donate. Each chlorine atom can accept one of those. That's why we have a 2-to-1 ratio between calcium and chlorine when we write the formula CaCO2, right? Now, one of the things we want to get away from with our ionic compounds, though, is picturing that as, a molecule, because it's really not. Really what it is, it's more something like this. So let's take a simpler compound, sodium chloride, right? It was just NaCl, right? One of each, right? Now, it's not that this sodium is directly linked to that chlorine with some sort of a shared orbital like we see in our covalent bonds, right? What we have typically is we don't just have a single sodium atom and a single chlorine ion just hanging out stuck together. What we have is a whole bunch of sodium ions and a whole bunch of chlorine ions that are all attracted to each other, right? And so what we get more is this structure where this sodium here is not just attracted to one of those chlorine atoms, right? It's attracted to all the chloride ions near it. And likewise, a chloride ion is not attracted to a single sodium, but to all the sodiums, near it, right? And so ionic compounds are actually just a big grouping of positive and negative ions that are all attracted to each other through those electromagnetic forces. So all those sodium ions are attracted to any of the negative chloride ions around it. Okay? Now, contrast that a little bit with our covalent compounds, right? They are actually connected to, right, by a shared orbital, these singular atoms, right? So in the case of like methane, ethane, and propane, for example, where they are non-polar, right? This carbon is technically attached to each of those 4 hydrogens, right? But it's not like it's attracted to a bunch of other hydrogens as well through electromagnetic attraction. Those are bonded together through shared pairs. And so once carbon, right, gets its 4 bonds that it's required, right, it basically doesn't have attraction to other particles, or very little attraction. All right. Now, what we have in between there is something like water, right? So water, so this would be a single water molecule, for example, right here, right? Now, water is connected, right, through covalent bonds, right? But because we have a polar molecule, right, where we have sort of a negative attached to the oxygen and a partial positive attached to the hydrogens, what we have there is also some electrostatic attraction to other water molecules. All right. Have you ever noticed how water tends to stick to itself? Right. This is sort of why. Right. And so what we have with our polar covalent bonds is sort of a mix of the properties of nonpolar covalent bonds, in that they are actually bonded and they have these actual molecules. So a water molecule of H2O is not just simply a ratio of hydrogen ions and oxygen ions. It's actually 2 hydrogens attached to a single oxygen. Okay? But with that, right, because we end up with some polarity, right, where we have imbalance in our polar bonds and some extra lone pairs on that oxygen, right, there's also some attraction from one water molecule to other water molecules, similar to the way that ions are. Okay, now, all that being said, right, so again, methane is not attracted to other methane molecules because it's nonpolar. Water is attracted to other water molecules because there is some partial electromagnetic attraction between them because of that polarity. All right, now, this leads us to a new term, right? Intermolecular forces. So we're talking about the forces that attract a molecule that's already got its bonds to other particles that already have their bonds, okay? And so, real quick, just a simplified version of talking about this. Ionic compounds, the attraction between particles is very high because they're full positives and full negatives, and so that a sodium ion is going to have a strong attraction to anything negative, like chloride ions, right? So there's a high attraction between particles. Now, in polar covalent compounds, right, where the bonds have already formed, so again, going back to something like water, for example, right, a water molecule has some moderate attraction to other water molecules that already has their bonds, okay? Whereas nonpolar covalent compounds, the attraction between molecules is low. Now, this is not talking about the bonds within the molecule. We're talking about the forces that attract one methane molecule to another methane molecule, right? Methane being nonpolar, the attraction between those two molecules is low, even though the bond between the carbons and hydrogens might be relatively high within the molecule. So intramolecular forces, right, are talking about the bonds that make the molecule. Intermolecular forces are talking about the forces attracting one molecule that's already got its bonds to another molecule that has similar bonds. Okay? Now, that being said, so we got high for ionic compounds, moderate for polar covalent compounds, and low attraction intermolecularly for our nonpolars. Okay, now we're going to relate this to boiling point to start, right? We'll come back with another lecture that brings us back to solubility and aroma, but just purely in terms of boiling point, right? We already know that ionic compounds have very high melting and boiling points. It takes us all the way back to the very beginning of Unit 4, okay? Now, we want to say why. Why is it that ionic compounds have very high melting and boiling points, right? It comes down to those intermolecular forces, that sodium ions and the chloride ions are very strongly attracted, not just to another one, but to all the charges around them, all right? And so in order for something to become a gas, so to make it boil, we're turning a liquid into a gas, for example, right? In order for something to become a gas, we have to fully separate, right, the individual particles from each other, right? Now, in order to turn something with very strong intermolecular forces into a gas, we have to have a ton of energy to fully separate those apart. All right, so we need lots of energy to overcome the high attraction between particles, which is why ionic compounds have high melting and boiling points. Okay, now contrast that a little bit with something like water. Water is a polar covalent compound, right? And so in order for water to become a gas, right, we need enough energy to separate those molecules from each other. So there's attraction, remember, between the partial positive on that hydrogen and the negative on that oxygen in another water molecule, right? So in order to separate those and break those hydrogen bonds, right, we need a moderate amount of energy to cause that to happen. And we can relate that to the fact that in order to make water boil, right, we need to heat it up relatively hot to about 100 degrees Celsius or 212 degrees Fahrenheit. Not super hot, but hot enough to make the point here. Now, contrast that with something like oxygen, right? Oxygen is already a gas at room temperature. We don't have to heat it up. In fact, in order to make oxygen not a gas, in order to bring these molecules close enough together, right, we have to actually get it super, super cold, right? So oxygen is non-polar, right, because there's no imbalance, right? It's a symmetrical molecule, right? So there is no, essentially zero attraction between those oxygen molecules. There's nothing really holding those together. So it's very easy for those molecules to be completely free of each other and be in that gas phase. And that's why a lot of the gases in our air, pretty much all the gases, are non-polar molecules. Carbon dioxide, nitrogen gas, oxygen gas, right? All of those have basically zero polarity and essentially zero attraction from one molecule to another. Okay? Now, it's not always that simple, right? So, for example, let's take paraffin wax, right? The size of the molecule actually matters too. Because again, so bigger molecules, right, are going to require a little bit more energy to turn into that gaseous phase. So paraffin wax, for example, fairly big molecule. That's one example of the paraffin class of molecules, right? C20H42, so 20 carbons and 42 hydrogens, right? And we recognize paraffin wax as basic candle wax, right? Now, paraffin wax is a solid at room temperature. Now, it's also non-polar. So why isn't it a gas, right? And simple explanation there is with our really big molecules, a little bit more energy is required to get them to move around a little more freely. All right? But we'll notice that paraffin wax, right, we can melt it at relatively low temperature. You can touch melted wax. And, I mean, it's a little uncomfortable, but it's not going to harm you too bad, right? And we can turn it to a gas, right? A candle flame is pretty warm, but not super duper hot, for example. All right? Okay. My computer's wigging out on me here, guys. Sorry. All right. Sorry, back at it. Little glitch there. Now, contrast that with something like sucrose. So sucrose is sugar, right? We recognize that as table sugar. All right, so sucrose is a polar molecule, right? All those extra oxygens in there add some polarity to that molecule. Now, sucrose is molecule similar in size to paraffin wax, right? Sugar is a polar covalent molecule, so we can melt it, right? But it does have a relatively high melting point, right? Not as high as something like salt would have, which is ionic, right? But definitely a higher melting point than paraffin wax, right? And then to get the sugar to boil would require an even higher temperature than paraffin wax to light a candle, for example. All right. So anyways, I hope this helps illustrate a little bit, make one connection for now between the structure of a molecule, whether it's ionic, polar covalent, and non-polar covalent, to something like boiling point, right? We will bring this back in the next lesson to things like solubility and aroma.